start the stream, and then I'll bring this up. And I'm fiddling with some stuff on my side. I was having a couple iPad problems, but I turned everything on and off again, and what do you know? Problems are solved. Hopefully. I say that now, but we'll see. Okay, so some things to remember for the week. Number one, we got a webassign coming in today. That webassign is about material in section 4.1 and 4.3. Good stuff in there, and that's where we learn about the homogeneous second order linear problem and the linear independence and linear combinations or superpositions. Also, I should note that there is a quiz coming up tomorrow. The quiz tomorrow, if you look in the modules on Canvas, you'll see that it's about 4.1, 4.2, and 4.3, but actually, excuse me, 4.1, 4.3, and 4.4, but we reconfigured some stuff, so know that it's just about 4.3, and that is the root finding technique, the solution finding technique, which we've been going over a lot these last couple days. So there are just a couple problems there to kind of test where that's at in your life, and maybe solidify some knowledge or motivate some more work in that area. And then there's a webassign coming in on Friday, 3/12, associated with putting MUC on top of those homogeneous problems. And this is a pretty good section of material. I feel that it's pretty cohesive, and we're about to drop into a new context, a new mathematical model associated with this. And so I'm excited to get to that today, but I need to push just a couple more buttons here on my end. And so bear with me a second. The screen might get a little wonky, but don't worry, I'll be right back. And then I will send out the stream source. There we go. There's that. My iPad's up and running. Let me get this web page up, and then I think I'm good to go. Yeah. Super exciting. It was looking pretty grim there for a minute. All right. Here we are. I'll bring this up, and let me see. Let's see if I can do it. Okay. Okay, that's there. That's there. And then one last thing, which is... here coming into chat is the stream link. All right. Keep letting me know if I'm a little quiet. I might have stepped away from the mic a little bit, but I can definitely raise the line levels. That's not a problem. Okay, so here we go. This is where we're at. We want to learn more about the method of undetermined coefficients, and we want to provide an introduction to mass spring systems. So, what's going on here? Oh yeah, I kind of went over the top a little bit on the mass spring systems, but there it is. And so, what do we need to know? We need to know, number one, this equation is the equation we're going to battle with basically for the rest of the semester. So get that firmly imprinted in your mind. Number two, it's a linear equation with an inhomogeneous term, so the solution is always the homogeneous plus particular. But since it's second order, this boils down to, with constant coefficients, a root finding problem. And because the root finding leads to two different types of roots, or I mean two different roots most of the time, and then a repeated root some of the time, the solutions to the homogeneous problem break into these three cases. One solution where I have an exponential defined by root 1, an exponential defined by root 2, and I linearly combine them. Then that root could go complex. They'd still be different. They'd be complex conjugates, but I would have a sinusoid representation because of Euler's identity for those complex roots. And so we need to know e to the real part t, cosine imaginary part t, plus e to the real part t, sine imaginary part, where you've got to be joking. Okay, Apple Pencil now registers. That's good. Whew. Where we have this real part, and imaginary part. And then the last thing here is that if the root is repeated, you get a second solution, which is a t multiplied version of the first solution. Okay, those are the three homogeneous cases. And then we've got to remember our MUC table and do battle with the rest. Okay, so I'm going to get back to the rest of this first slide in a second. I think that it's probably just a good idea to dive into a problem right away and shake off any of the cobwebs. And so let's do that. That'll also get me a chance to get my head together. Okay. So I'm going to put a minute timer up. With that minute timer, find the solution to the homogeneous problem. And from that solution, or from that knowledge, try to set up the particular solution, please. All right. So I'll take that minute timer off. And so what do? I plug in e to the RT into the homogeneous equation, which means I set this right-hand side equal to 0. Once I plug that e to the RT in, I get this quadratic equation, and now I ask myself what numbers will add together to be -1, but multiply together to be 1/4, and that is going to give me an r, let's see, -1/2 times an r minus 1/2. Let's double check. -1/2 times -1/2 is a 1/4, and then -1/2 plus -1/2 is a -1. So I'm good there, except that r is a repeated root. R is equal to 1/2. R being 1/2 is the root value, so that both of these parens will vanish. Okay. Next, I'm going to write down my homogeneous solution. It is a function of x. That is the independent variable. So I get c1 e to the 1/2 times x plus c2 e to the 1/2 times x. I look at those and I'm saying to myself that they are the same function. Therefore, they are not linearly independent. And to make the second solution linearly independent from the first, we multiply through by x. Okay, so for those that are feeling more comfortable, I'll refer you to the book, and it has a derivation, and by derivation I mean that it's a general result, and it's called reduction of order. The idea with this, right now we need to know that we're just going to multiply the second solution by the independent variable to make it linearly independent from the first solution, if we have repeated roots. And you might wonder, where does that come from? Is there a more first principles approach to that? And yes, there is. It's called reduction of order. And the idea is that you can bootstrap off of the first solution and construct the second solution from that through a sequence of integrals. It's a really good time, trust me, but the general rule of thumb that comes out is you get this x multiplier, making the linear independence. Okay, so now I have this f of x, not f of t, I have an f of x right here. And with that f of x, I need to choose the form for my particular solution. So my particular solution, what's it going to be like? Well, I see a constant 7. I say, well, the particular solution should have some sort of function within it that models that constant. And so I see a constant, and I write down a constant to account for that. Just as if I see a linear function, I write down a linear function, the most general linear function to account for that. Next, I see an e to the x over 2. So what would my normal pick be? It would be b e to the x over 2. Okay? But I gotta tell you that this is not right. Does anyone know why this might not be correct? And I'll at least point you in the direction of what's not correct. What's not correct is right here, underlined in red. The X? Yeah, okay. The X is missing. Okay, good ideas in there. We got some X multiplication that's coming around in some people's heads. I'm also getting a comment that it's the same as the homogeneous solution. And so let me actually highlight that, and I'll erase this underscored red here. I will get a color out. I'll get the color purple. I'll underline this in purple, and I'll notice that it's the exact same function as this exponential right here. So correspondence to y1, I'll just say. Okay. Well, what would that mean? I'll use a purple implication sign, and that means I should make an upgrade. What is my upgrade? Okay, my y particular is now going to be the a. I wasn't really having a problem with the a, so I'll keep the a. And then this be to the x over 2, that totally looks like the first of the two homogeneous solutions. So what am I going to do? I'm going to multiply by x to force it to be linearly independent from the homogeneous solution, the first term in the homogeneous solution. And then I'm going to follow this up with a statement saying this is not correct either. All right, why is this not correct either? Well, for those following along, I won't ask for it in chat, but check out this xe to the x over 2. If I were to add this onto the homogeneous solution, it would just get absorbed into cxe to the x over 2. It'll just get absorbed into this function right here, right? Yep, and you're sussing it out in chat. That's absolutely great. So now I've got to make a choice here that is different than this homogeneous solution, the second term now. And so this corresponds to y2. Okay? And so the third implication now is, okay, I've got to write down y sub p of x. This is going to be a, which is just as it was before. There's no problems there, but then I have to add b times x squared e to the x over 2. Okay, this x squared has come about because I need my particular solution to be linearly independent of the homogeneous solution, and this same exponential corresponding to this exponent of 1/2 coming from the homogeneous just keeps coming up, so I've got to keep x multiplying onto it until the linear independence is forced. Okay. So I will point out in brown right here that now this is linearly independent. Of y homogeneous. Okay. All right. Questions about that? All right, with this x squared right here, and feel free to chime in. I know I'm just moving along and I gave it like 5 seconds, but just feel free to ask. This x squared that's right here, this x squared is not like the ax squared plus bx plus c like we had seen in other problems. This x squared is coming totally for the purposes of linear independence, and so I don't do an expansion like I would have if I saw an x squared. Yep, so it couldn't be x or e to the x over 2 or xe to the x over 2 because they are in y homogeneous. Absolutely correct. So I'm going to highlight in brown those two features. The x squared is coming out because of linear independence. Okay. So we keep putting x's on until we have linear independence. That is the case. That is true. You might ask yourself, well, this is getting pretty sketchy. Why would I do that? What compels me to do that? And there is another derivation. It is a very classic derivation called variation of parameters. So I'm going to drop that little note here. And so let's talk about that really quick. Think about how far we've come in terms of solving what is inherently a calculus problem on derivatives, and look at the work that we have mapped out here and the work that we've been doing. We haven't done any integration, right? You would think that to solve a differential equation, you would need to integrate somehow, but we're not doing any of that, right? Well, it turns out reduction of order and variation of parameters are more classic techniques, more abstract techniques that rely on integration to find the solution. And just like the method of, or the integrating factor method taught us about the method of undetermined coefficients, these integrals that are in reduction of order and variation of parameters will show us the exact same patterns. And so once those patterns are established, you chuck those integrals because they are rough and tumbly, and you just get down with the patterns. And right now we are looking at one of the oddball cases for MUC. Okay. Why not just change the x in the exponential? That's a good question. But if I change this value in the exponential, when I take derivatives and plug it back into the equation, say if I had x or e to the 8 or 9x over 2, that won't ever match up with this e to the x over 2, and so you're not going to be able to balance the equation and find your coefficients. Good question. That's a common question. Okay.
How many more times can we continue to add x until this breaks?
It won't ever break. Well, I mean, okay, let me answer the question in two parts, Nate. One, if I were to just go crazy and be like, I'm still not sure about the x squared, I'm going to make it x cubed, I would find out that I'm wrong, okay? And then I would go back and be like, maybe I should back off of that a little and use an x squared instead, because that's where I was last left. For our purposes for second order, I'm only ever going to get an e and then maybe an xe right here. So for the particular solution, I'm only ever going to see x squared. That's the highest it can go for second order. If we were to get into third order, you might see cubes, but you have to increase the order of the ODE to see that.
Okay, got it. Thank you.
Cool. No problem. All right. So now let's try to find A, or let's try to find B. And so let me up here start the MUC process. With the MUC process, the next piece that I'd like to talk to you about is the following, and that is we can do this in two pieces. What two pieces do I mean? I could call this here maybe YP1. The notation here is not going to be great, team, but I'm going to highlight the notation right here, and then we're just going to cavalierly do our work. I could call the first term y sub p1 and the second term y sub p2. And why would I do that? I would do that because I don't have to take the whole particular solution, take its derivatives, and plug it into the diffie-q, right? Because when I do this, the A will only ever try to match up with this 7, and this exponential gobbledygook right here will only ever try to match up with this exponential. So what I can do is I can find A just on its own through MUC, and then I can find B on its own, and I don't have to make this huge horizontal line of text. So if I have y sub p2 is equal to A, then that implies y double prime sub p2 plus minus actually y prime sub p2, and you might not want to write it as p2, but however you want to organize your work so that you remember what you're doing, that's the important part. And then 1/4 y sub p2, and that is equal to, well, what's the second derivative of my constant A? Goose egg, bunch of nothing. Oh yeah, p1, sorry, p1s, thanks. Already seeing complications due to the notation. And I don't care if you write down P1 or P2, you just got to keep your work organized so that you don't get it all mixed up. Okay? Thank you. The second derivative of my constant A, that would be 0, minus the first derivative, well, that's going to be 0, and then plus 1/4 times A. And what should all of this be at the end of the day? It should be equal to, I'm going to write it down here, it should be equal to 7 plus e to the x over 2. Okay, so that's what I mean when I say that these will not get mixed up with each other. This 1/4 A can only match up with this 7. This 1/4 A will never be like an exponential, so this exponential just hangs out. It's not getting used right now, and so that's fine, because what I have at this point is knowledge about A, because A is equal to 4 times 7, so what A is equal to 28. Now, I've avoided the fun part, right, which is the second particular bit. And so let's check out that second particular bit. I have y sub p2 is equal to b x squared e to the x over 2. I'm trying to figure out where to lay this out so that it's halfway decent to work with. And what I'm going to do is I'm going to move it. I need some vertical space. And so I'm going to move it over here, because what I'm going to do is I'm going to play that stacking game again. What do I have to do to put this into the differential equation? Well, I'm going to have derivatives to take, and a lot of product rules are about to come up. So I'm going to give myself some vertical space and just make a stack here. With that stack, I have y sub p2 prime. But what is that? That's b times, okay, take the derivative of x squared to get 2x times e to the x over 2, and then leave the x squared alone and take the derivative of the e to get x squared over 2 times e to the x over 2. Like that. All right, and then I'm going to get y sub p2 double prime is equal to, okay, I have this b out front again, so I'm going to have that b out front. Now I've got to use a product rule here. And I've got to use another product rule here. So there are going to be 4 lovely terms coming out of this mess. I take the derivative of 2x to get 2e to the x over 2, where I've left the e alone. Now I leave the x alone, take the derivative, so I get a 2 divided by 1/2, so I get, or I mean divided by 2, so I get 2 over 2, and then I get x e to the x over 2. And then, okay, I take the derivative here on x squared. A 2 comes out front and cancels with the 2 in the denominator, so I get plus x e to the x over 2. And then I take the derivative of e, leave the x squared alone, so I get x squared over 4 e to the x over 2. And then I step back, I take a breath, and then I kind of steal up for the next part. Okay. I don't have any water here, so I'm going to pretend drink my water that I normally have. All right. Hopefully all my terms are correct, because what's about to happen now is going to be pretty magical. Because this is the hardest we've worked to get a butt ton of zeros. We're about to get a ton of zeros out of this. So, what am I going to do? I'm going to put my horizontal line down. I'm going to add these things up. I don't want exactly these things, right? Because I want 1 much y double prime, because there's a 1 right here in the differential equation proper. Okay, and then I want negative 1 times y sub p. And then I want plus 1/4 times the no derivative term. Okay. So at the end of the day, what is all of this going to equal? All of this is going to equal what's on the right-hand side of the differential equation. So I'm going to write that whatever comes out of this stuff better be equal to a 7 plus e to the x over 2 at the end of the day. Okay. Here's the rub. Over here on the right-hand side of my differential equation, I have an e to the x over 2. Over here on my left-hand side, once I add all these together, I got loads of gobbledygook, and some of that gobbledygook has x times e to the x over 2 and x squared times e to the x over 2. There are no functions like that on the right-hand side, right? So if they hang around, they're gonna mess up the coefficients. So what I have to do, well, I mean, I don't have to. What I have to note here is that those terms are going to go away. Let me highlight those terms here in red. This term's marked for deletion. These terms I think are marked for deletion. This and this and this. I think all of those terms are going to vanish. I hope so, because, I mean, otherwise we got problems and I did something wrong. But let's check it out. There's an x squared term. There's one much of it. Actually, 1/4 much of it. Here's an x squared term, but there's another 1/4 much of it. So what is that going to total? If I add 1/4 of that x squared term plus 1/4 of that x squared term, I'll have 1/2 of that x squared term. But then check out what happens here in the middle row, the -1 times. What am I going to get when I multiply that gray -1 in? I'm going to get -1/2 x squared times that exponential. So this term and this term will cancel out this term coming from y prime. And then what do I have here? I have an x e to the x over 2 plus x e to the x over 2, giving me a grand total of 2 x e to the x over 2's. But look what's happening right here. What's happening right here is I get -2 times x e to the x over 2. Those terms cancel out as well. All the red stuff goes away, leaving behind only 2 times b times x e to the x over 2. So what does that tell me? That tells me that my b is equal to 1/2. All right. Do I have my a? Yes. Do I have my b? Yes. So I have all my unknown constants. Let me point at the right ones, right? This third iteration is the right one. I have my a and b. I know all my undetermined coefficients with the particular solution. And so I add that to the homogeneous solution. And that is my final solution, which I'll do right now. I see that question in chat. I'm coming back in there. Y of x is equal to c1 e to the x over 2 plus c2 ex e to the x over 2 plus 28 plus, now be careful with this whole line of logic here. This b that I found goes in my third option, so I get 1/2 x squared e to the x over 2. Okay, and that's a high watermark for the method of undetermined coefficients. That's about as kooky and painful as it can get without just loading up the f of x function with just a ton of terms. Okay. All right, so question coming up in chat, why don't we need the other terms after bx squared x e to the x over, or e to the x over 2? Wouldn't we also need the c and the d? Oh yeah, that is a great question, Jules. Jules, what's going on there is that this x squared came up because of multiplication to make linear independence, not because of that power function rule that you're quoting with the x squared, the x, and the constant term. Don't confuse those two. These x's appeared not because of a table rule, but because of a way to correct for an independence issue. Yep. And is b equal to 1/2 because 2 times 1/2 is equal to 1 much e to the x over 2? Yeah. Cool. Cool. All right. There's one more kooky method of undetermined coefficients problem that I'm going to need to tell you about, but right now, nah, I don't know. Maybe we should do it. I think we should do it. Okay. I'm going to do it. Let's get this all frozen here. Take any last notes that you might like in about 10 more seconds. We will do one more, and then we'll transition into context. And that way we'll leave off class today with a little bit of fun, I think. Not that this wasn't horribly fun. All right, transitioning over to the next screen in 3, 2, and 1. Coming back in. There we go. So we have the method of undetermined coefficients table. We have the idea that if you see things that are added, you guess their parts and add them together, and that's your new guess. If you see things that are multiplied, you guess their parts, you multiply them together, that's your guess. We see this x or t multiplication to get linear independence. Okay? So one last situation that can come up now that wasn't coming up for first order is the following. And so I'm going to give us a minute on the timer again, and why don't you set omega and omega naught equal to 2 and f is equal to 2 and solve the problem. So let me write down the problem with those substitutions, and that is going to be y double prime plus 4y is equal to 4. And I want to change this omega naught actually. No, I'm cool with it. 2 times cosine of 2t. Okay, I'm going to re-up that since I jabbered through it. Okay, I'm going to bring the timer down. Feel free to keep working. Something I'll mention that I don't think I've mentioned before, and I'm going to put this back out in the chat again, is that in the stream that's going on YouTube, something that I see data of here that is probably useful for you to know is that while the live stream's occurring, I think you can click backwards in time. And so if there's something that happens and we get one of these 1-minute windows and you want to go back and check, that's an available option. So I write down my homogeneous or the characteristic equation for the homogeneous problem. I get r squared plus 4 is 0. That means r is equal to plus or minus the square root of negative 4, which means I get plus or minus 2i. Okay? So that means, okay, my homogeneous solution is a function of time is going to be, well, what happens when I get i's? I'm going to get c1 e to the alpha t times the cosine of beta t plus c2 e to the alpha t plus times sine of beta t. But what's my alpha? In this equation here, there's no real part, so my alpha is equal to 0. But then what's e to the 0? My e to the zeros are 1, so I get c1 times cosine beta. Well, what goes in for that beta? It's the imaginary component to the complex root that goes in for beta, so I get 2t plus c2 sine 2t. Okay. The particular solution. My f of t is equal to 2 cosine 2t. Someone in chat tell me, based on our table from first order, what should I write down for my particular guess? Yep. I see an A cosine 2t plus B sine 2t. And that's coming from first order saying if you see a sine or a cosine of a specific frequency, then you write down particular solutions as cosine and sine pairs. A question that comes up here is, does it matter whether you put the A on the sine or the B on the cosine? Doesn't matter at all. Okay? Yeah, and Asher's coming up with in chat, right? And I'm reading some of the other chat messages coming into me right now that you still have to change it to t multiplying these cosines and sines. And you're exactly right. Looking at this cosine of 2t, that's identical to one of the two functions in the homogeneous solution, and the same thing with this sine function. So this, just as before, is not correct. So what does this tell me to do? Well, the rule that I have is I need to take these functions and make them linearly independent by multiplying them by t. So while it is totally reasonable and possible to have t's or x's multiplying exponential functions, because we're in second order now and we get to sines and cosines as solutions to the primitive homogeneous problem, I can still end up with that t multiplication situation. Garrett's asking in chat about dividing by a 2 in the quadratic equation. And Garrett, go back and check out the quadratic equation proper, and you'll see some cancellations that happen. The root here is definitely just from without quadratic equation algebra plus or minus 2i. So if you write out the full quadratic equation, you'll get the same result. There's something in there it's probably like b squared, which is 0 minus, there's an extra 4 in the discriminant. Yeah, there you go. Cool. Okay, cool. That is addressed. So let me talk about why this is important. And so now I have a visual aid, but let's talk about it this way. For the homogeneous solution, say for some reason you got some initial conditions that when you solved for the constant C1 and C2 after adding things together, you found that C2 was 0 and C1 was the number 1. Just for the homogeneous solution, as time gets larger, can you tell me what the homogeneous solution's going to do? Well, probably not really, because when time goes to infinity, the cosine function's not defined, right? I don't know what's going to happen, but I do know the following. If this C2 is 0 and that C1 is 1, what's the largest in positive numbers that the cosine function's ever going to be? 1. Okay, what's the largest in negative numbers it's going to be? -1. Okay, so as t goes to infinity, can we at least agree that this homogeneous solution, it's going to have C1 and C2 for amplitudes, but those amplitudes are going to have sines and cosines multiplying them? And so they're never really going to get any larger than C1 in magnitude or C2 in magnitude. I'd have to do a little bit more trig to figure out what the combined amplitude is, but what we want to recognize here is that this is bounded as t goes to infinity. Okay? And then here, looking at this function, this particular solution, I'd play the particular solution game to find the a and b, but even after I find those a and b's, what's going to happen to the amplitude of this cosine function as time gets larger and larger? What will the amplitude of the oscillation do? Okay. This is a hideously important result. And so let me exemplify the result right now through a demonstration. In the demonstration, it isn't a physical system that we're going to deal with, but it can be approximated with one. And so here's the physical system. This is a Tibetan singing bowl. It's made of copper, and I can do this. Notice that it is acting on its own. After I hit it, at least, right? After I disturb it, it is acting on its own, right? And how is it acting? It's making a sound at a particular tone. What is a sound? Well, it's going to be the oscillation of the molecules in the air, right? And those oscillations are going to be periodic in time. So if I were to just displace the system, this system, upon being displaced, wants to oscillate. Okay? Now, what happens to those oscillations? This is pertinent. Yeah, Ryan. Yeah. What happens to those oscillations in time is that they naturally decay because there's some sort of decay mechanism. But now, what's going to happen is that the system is going to respond to some sort of external force, and this is what I can do. Here's the external force. Here's the system. I hit it. And so, when I hit it, I send it into motion, and it's an oscillatory motion, and then I come in with the stick and I try to support that oscillatory motion when it wants to, or throughout its life cycle. What I'm doing is I'm resonating the bowl. I'm adding energy to the bowl in a constructive way so that the amplitudes of the oscillation increase as time increases. Okay? So I would argue that of all the method of undetermined coefficient problems that we've mathematically done, this is the one that is the most interesting. And that is because it has a constructive effect to oscillate the bowl at larger amplitude, right? This is the reason why they want to say the Tacoma Narrows Bridge goes down, right? This is a ubiquitous physical phenomenon and one that is very important for a variety of engineered systems, okay? I just have a bowl, right? So, what sort of engineered systems are those? Well, let's cut over to Canvas, where on Canvas I would like to show you some stuff that's been laid out. And what is that stuff? Okay, where am I going to go? I'm going to go into section D here. And if I go into section D, this is what I'll find. Okay? From the summer of 2020, I did a very lengthy derivation of the following situation. Take the ceiling, attach a spring to it. The spring is ideal. Put a mass on that spring. You can pull the spring mass down and let it go, and you can observe the oscillations. Okay? Now, that is the derivation for Newton's second law, and there's discussion in there. I'm going to pick up on some of this, but I'm not going to do the whole tale, right? Because it's a lengthy tale, and it's there if you want it. What we want to do is look at the observed physical phenomenon. And so, first pass, there's some media. Why might you want to look at the observed physical phenomenon? Well, let me pop this out. I guess I should have given it a name. But let's click that random link. And this is what we have. This is an image stabilized video of a Baja racer. Okay? What is this Baja racer? Well, it's a cockpit and it's got 4 wheels, and each of the wheels is going to be attached to a shock absorber. A shock absorber is a spring, and inside the spring is this thing called a dash pot. Best place to find one of these things, if you have a screen door that automatically closes and you go and look up at the top of that screen door, you're going to see a hydraulic mechanism, which is the dash pot, and a spring to pull it back. Okay, but these sorts of systems are around all over the place. This Baja racer has 4, and so why might we want to consider this physical system? Well, this Baja racer is flying through the desert, right, and it's got this spring inside of its wheel well with a dash pot in it, and it's got this tire. The mass is the cockpit, the car, and the external force is the ground that's pounding up on the tire. Okay, now that's the system. Let's think about the practical nature of the system. As this person in the cockpit, what do I want to have happen? I want my tire to return to the ground as quickly as possible. So I want to configure my mass, my spring, and my damping, my dash pot, so that that tire is driven back to the ground as quickly as possible, because without the tire on the ground, I'm not going to be able to steer and I'm not going to be able to put power down, right? So fiddling with these sorts of things is very important for a variety of physical phenomena. So I will also tell you that there's a YouTube playlist right here, which has a variety of different oscillatory phenomenon that can be modeled by mass spring systems. And then here's another one. Don't worry about that, but feel free to look through these things and look back at this derivation. I will move on to this first slide now so that we can take a look at the governing equation.
I have one question.
Yeah, what's up, Nate?
So since this is an increasing amplitude as it gets larger, I want to say like the inverse of this is like, because the Fourier, right?
Maybe. We should chat offline. Fourier is not necessarily not a topic in the course, but it's dicey to kind of get into live because it's so fun to talk about, but I'm going to burn down a lot of time if we chat about it. So yeah, let's talk after.
Okay, sounds good.
No problem. Let me show you now the following equation. I would like to direct your attention to right here. And so, if I were to look at the forces in play on that mass spring system and apply Newton's second law, this is the equation that I would get, where m is a constant, b is a constant, and k is a constant. And so this differential equation is exactly the differential equation that we've already got a full plan for. Okay, so if I were to look at this differential equation, this is m times y double prime, but isn't that the same thing as mass times dv dt? Right? If v's velocity, then its derivative would be the second derivative of displacement. This would be the acceleration. And then if I move all the other stuff over to the right-hand side, this is going to look like negative b times y prime minus k times y plus f of t. So why does this equation come from physics, or how does it come from physics without doing the full derivation? This term right here represents force net. Okay? This term right here, tell me, well, if y represents displacement, what does y prime represent? Velocity. Okay, what is a force that is proportional to how fast you're going? Think about driving down Washington Avenue at like 30 miles an hour versus driving down I-70 at like 80 or 70, whatever the respected speed limit is. Air resistance. So this term here deals with drag, or what is often called damping. Now you've got a mass tied to a spring that's ideally elastic, that's allowed to move up and down in space and experience drag. From your physics class, because I think Phys 1 should be had by now, or you might be in it, what is the force, for people that know, that is proportional to displacement? Yes, this is the spring force. And then this f of t right here doesn't have to do with any of the system properties. It's just hanging out in space. And what would that be? If this is the mass moving up and down, there could be some science person poking it with a stick. Think about pushing somebody on the swings. F of t is the external agent that's pushing the person. This is the external force. So it turns out that this equation that we've been dealing with is exactly the equation that you would get to if you modeled in very idealized circumstances the motion of a mass tied to an ideally elastic spring subject to air resistance and poking by some sort of external agent. So the inhomogeneous term we now think about is an external forcing function, and the autonomous problem, the homogeneous problem here, is what would the system do if you were not poking at it? Okay, so we want to take that intuition going into Friday's lecture, where we will model and talk about the vocabulary of mass spring systems and look at more demonstrations. But that's all for today. Have fun. See you on Friday.
Recording stopped.
Oh.